progress in any thoughts. And so I really missed it. And the thing I look forward to the most, I think, is not only just the talks, but the informal discussions that happen afterwards over beer and things like this. And so I thought, wow, I'm really going to miss that. And I said, what would I like to ask everyone there? I would like to ask them about the question I'm going to talk about tonight, or this afternoon, I should say, which is the title of my talk: Who is Oliver Consa, and why is he wrong about QED? That's what I would want to ask everybody, if they've heard of this gentleman, and his thoughts regarding quantum electrodynamics, and what do you think of it? That's what I would be asking everybody, because I want some clarity in my own thoughts, because I don't want to be stuck in my head about this. So that's what I'm going to talk about. Now, if anybody knows Professor Consa, who's in Barcelona, I've never met him. I don't really know much about him other than his work. If anybody out there knows him and knows about him, then you may be able to introduce some clarity at the end of the talk. The other thing I wanted to that I've learned over the last 2 years is that I think I've wasted my entire career thinking I was a theorist when I really was meant to be an experimentalist, because I love talking about numbers. I love talking about measurements. That is where my heart is, I realized. And so yeah, I'm just in awe of people who can derive interesting equations that tell us about the universe. But my mind is always, what numbers do they give out? That's all I'm always thinking. And it's like, oh, you know what? I should have been an experimentalist, but I was too lazy to go into the lab. So tragedy, but life goes on. So yeah, so we're going to talk about some numbers. We're going to talk about experimental values of the magnetic moment of the electron, how it differs from unity, the Bohr magneton. I think I'm sure everybody's familiar with this and its role in the history of quantum electrodynamics. And we're going to talk about some theoretical numbers too. We're talking about theory and experiment. And so I just put those numbers up there to give you a preview of that. I borrowed this slide from Asher, who was just showing it. Thankfully, he had very readable slides, even though we couldn't hear him, and I was able to get a lot out of his talk, but I really did miss it. The Williams Ockham, I just stole this from him. Law of parsimony, always something to be inspired about. First, before I get started, just a moment of levity. Trivia question: Who said the following and to whom? So this is a question for you all. Who said the following and to whom? There is somebody in the audience who knows the answer to this. I'm not going to give it away, at least not right now. But the question is, the quote is, "I didn't let Richard Feynman get away with that, and I'm not going to let you get away with that either." Is the quote. Somebody out there knows the answer. I'm not going to say who and what context, because it's their story to tell, not mine. Feynman, yeah, we'll talk about him. Crazy character with the misspelled license plates and a van with all his diagrams on it, which represent radiative corrections to scattering processes, as we know, and changed physics, really defined post-war physics. And he drove this van around, and I guess it's been kept and restored, that he used to drive there. Yeah, Feynman diagrams, they remind me of, let's see, get this name right, Kitsugi, the Japanese art and appreciation of broken objects that have been mended. And I look at Feynman diagrams, and there's something about it in these brokenness of this that I see this. And I think that's sort of appropriate, because it's sort of absurd. And Feynman, well, he thought nature, we should accept it as absurd if it comes out to be looking absurd. And this was one of his rebuttals. This is from his book, famous book QED, that he published in 1985, shortly before his death. And so he was not a lover of the notion that nature had to be beautiful, that it might just be sort of ugly in its mathematics. And we'll talk a little bit more about this. So who is this? This, as you know, this is another question. This is Isidore Rabi. And who would have thought 2 years ago, when we last met in Prague, that by the time we met again, there would be a Hollywood movie that would win the Academy Award for Best Picture, and one of the supporting characters would be Isidore Rabi. I mean, who would have thought that? Not to mention all the others that are in there. But I thought Rabi was played very well. I never met him, but I thought it was very well done. And it's almost like we're talking about the I fantasized about making a sequel to Oppenheimer in using the same actors and in the same narrative universe. And this is sort of the subject would be the stuff we're talking about tonight. So, who is Oliver Consa? He's at the Polytechnic University of Catalonia. He's got a website, private website. I would not suggest going to his website before you read his papers. It will prejudice you against him. If I give one word of advice, I say if you're a physicist who has heterodox ideas that sort of go against the mainstream, which Concept certainly does, I would say don't make a website that's very flashy, because it will not be to your credit. So but he's got stuff on ResearchGate, and so what's wrong with why is he wrong about QED? Well, what does he say about QED? He says a lot about QED, and he's in several papers that he's essentially, he published one in Progress in Physics a couple of years ago, and then he's got a couple preprints, and it's the preprints where he sort of keeps rewriting them, making them more refined, and releasing the preprints. And a lot of his heart of his argument is in the preprints, and you could sort of see why. He's very controversial. He writes in a style that sort of makes it could be hard to publish some of his things. And so I wanted to give you an introduction to his work in case you hadn't read his work. His papers, the ones we're going to look at: Searching for the Feynman Diagram 2C. That's the diagram you see on the screen, by the way. And Something is Wrong in the State of QED. These were fall of 2021, but they were really written before that, and these are the latest versions, I think. And it's good that he's revising them, I think, because I think he's still fleshing out his argument he's trying to make in these papers. But they're very interesting arguments, and I learned a lot reading them. The third reference he originally titled "Something is Rotten in the State of QED," which is very provocative title. Of course, it's quoting Shakespeare from Hamlet. Nevertheless, it's rather provocative. So I think he toned it down when he submitted a updated preprint to Archive, which, as you know, has almost now become the Journal of Physics in a way. So, what is his essential thesis? Let me just get a few things out of the way. He's very controversial in his ideas about quantum electrodynamics. Why is he wrong? I don't know. I can tell you that right away. I don't know why he's wrong. I was sort of hoping other people might tell me what their opinions about why he's wrong, because I don't know. So I'll get that out of the way, and I'm not going to be able to tell you why he's wrong in this talk. I'm just going to sort of leave that question out there for people. But essentially, he's going to say that there is something wrong with QED, very fundamentally wrong, and that it has to do with the I would say this, that there's sort of a he uses the word fraud, which is very strong, and so let's not use that. But I don't know, shenanigans maybe in terms of the calculations of the terms of the magnetic moment, which are not quite on the up and up, and we may have been led astray in this very notion that quantum electrodynamics is the most accurate theory ever put forth, which is something that we hear, right? Because of the unprecedented accuracy of the predictions of the electron magnetic moment, that it's 12 decimal places and growing with every passing decade. And isn't that great? It's so wonderful. And he says, no, I don't. He says, I don't think that's true, and I'm going to give a case for it. And I would say, just to give you an advance, because all I can do is give you a summary here, I think, of his arguments. It's not going to be a satisfying deep dive, unfortunately, with the time constraints we have. But I will say that, and my knowledge of it too, I'm still figuring this out. So I'll be honest with that. That there is he says there's something going wrong here with the way we're calculating this, and it's basically, I would say, his central thesis is that quantum electrodynamics, as formulated by Feynman and is used since World War II, it has become a mechanism for calculating arbitrarily precise numbers that match experiment as experiment is refined. I think that's his central thesis of his papers, and he's going to try to do that I think he builds what I would call a circumstantial case for it, looking at the observations, the experiments, and looking at the theoretical predictions. It's a circumstantial case, but with some strong points to it. I will say he has some strong points that make one think, if nothing else, about what's going on. But by extension, by impeaching the underlying validity of quantum electrodynamics, he's going to then say, well, yeah, but we're talking really about Feynman diagrams and whether they can be actually, whether they're valid to represent nature. It was a very, very controversial statement, right? And at least now, wasn't originally when Feynman proposed it, which we'll see in a minute. But it would be very controversial now. And in doing so, he's going to, dare I say, attack the validity of the Standard Model as a whole. I would say that he does that. He doesn't go into depth about that, but he just basically says if QED isn't valid in its formulation with Feynman diagrams to predict the electron magnetic moment, then how can we say that its use in throughout the Standard Model is valid too? I think is his point there. And another thing about he really dwells on, stepping back in his macro approach, he brings up points that many other people have made in regard to whether or not it is at all valid to use renormalization in calculations. And he goes back and he's going to look at the early critiques of renormalization from physicists at the time. And of course, I think we're all aware of these things, all of us, but he's going to say, hey, come on, let's really examine whether this is sensible to use this techniques or not, in a way that harkens to when QED first was introduced and when quantum field theory was first introduced. So if you're interested in that topic, in that kind of critique of theory, I would say these are really interesting papers to read. So renormalization, yeah, he dwells on it a lot. He's got a whole sections on sort of summarizing the different ways you use renormalization, substitution, separation, cutoff, substitute. Really was introduced in the work by Beta on the Lamb shift of taking in what was an infinite series and saying, no, I'm going to assign a value to it that's finite and come up with the right answer, which is, of course, the big defense. The big defense of all this is, hey, we get the right answer. And he say, well, maybe you do and maybe you don't. Maybe you just think you get the right answer. Is I would say the theme of his work. So let's talk about Shelter Island, 1947. Well, actually, and Robbie was there, of course. But first, let's just go back, let's step back a minute. Let's give it a little perspective in time. 1921, The Magnetic Electron by Compton, a paper. He wasn't the first to introduce the idea of the magnetic properties inside the atom, but this was a landmark paper introducing the idea of this was orbital spin, though. It would take a little bit time, a few more years to come up with the concept of intrinsic spin to accompany this. But the time frame's interesting. 1921, of course, the 20s were just incredibly fast developing time. By the end of the decade, you have the Dirac equation. Probably, is this the most beautiful moment in the history of theoretical physics, the Dirac equation? The last perfect moment of theoretical physics? I don't know. It sort of feels that way. But so just a little perspective. Yeah, quantum theory of the electron. And of course, Dirac's great triumph was in being able to predict the hyperfine structure of the hydrogen atom, which had been known since, I guess, the 1880s. I didn't know this, but I was just looking it up. Michelson-Morley. So late 1880s. And Dirac solved it. And so it stands up there, right, with Bohr. Of course, Bohr solved the n level, and then we got to this. And so what more do you want out of a theory than that? So now let's move forward. Shelter Island, or after the war, and Consa makes a lot of statements like this: if Dirac had been at the Shelter Island conference, ... well, things would have been a lot different. And he wasn't. So this is sort of a theme. So there, in his work, what's it called? Something is wrong with the state of QED. He has a rather interesting introductory section which goes into the history of the development of QED in a way that's nicely put together, referenced with physics history. It is history of physics at this point, which is, you know, we're are we so comfortable talking about that it's important to talk about the history of how things were developed? We would like to think in physics that it really doesn't matter, right? It doesn't matter. We're talking about nature. It doesn't matter who did what and when. But because of this, he's putting this circumstantial case together regarding the predictions of the magnetic moment of the electron. He's going to need to he wants to build up sort of a background case. So he does do some research into the history of physics, putting together testimony of people that were there. Of course, there were 24 physicists there. They were from the Manhattan Project. Oppenheimer oversaw it, and Bethe, Bohm, Bright, Feynman, Kramers, Lamb, von Neumann, Pauling, Rabi, Schwinger, Teller, Uhlenbeck, Weisskopf, and Wheeler. All of them were there. And it's, of course, everybody knows about the Shelter Island Conference and its importance. Two important experimental measurements were presented, the one we're talking about here. But the Lamb shift by Willis Lamb, 1,000 megahertz difference in two lines in the hyperfine structure that should be degenerate were found to differ by a 30 centimeter line. And then there was Rabi with his team who said, well, there's also discrepancy in the hyperfine structure. And so these are Consa's words here. Meeting participants assumed that Dirac's theory of the electron was incomplete and proposed that effects were due to the quantization of the electromagnetic field. It was assumed that these discrepancies could be calculated and that the infinities of this theory could be corrected using renormalization techniques. This was the origin of quantum electrodynamics. So he's a little ambiguous here in terms of how renormalization comes into the theory. And maybe I'm hitting the soft underbelly of my ignorance at this phase of the history of quantum field theory. We do know that Bethe uses the renormalization. So the Lamb shift, differed by about 1,000 megahertz. And then Bethe says, well, I can solve this. He was on the train back home. He said, I think I can solve this. And he supposedly cooks this up, and he's got this infinite series and gives it the term, says, I'm going to give it the value of the rest mass of the electron. And even though it's a divergent series, and it's an infinite series, divergence to infinity is the right, its limit is infinity. That's right. And it matched. It came up very close to the experimental value that Lamb and his team had measured, and there was this great excitement. And Freeman Dyson says this was the golden age of post-war physics. Was the days of figuring out the Lamb shift, and he publishes it, and everybody's really excited about it for a while. And of course, Rabi publishes his work. And then Bright interprets it as being the Rabi's effect as being due to an anomaly in the magnetic moment of the electron, right? So, and we get this. Out of this we define from his work. I think this is in his work. I'm not quite sure. The ratio of the magnetic moment of the electron to the Bohr magneton. And forgive me, there's an ambiguity here between G being 1 and G being 2, according to the Dirac theory. I'm going to use G equals 1. So that's the ratio, and so in the Dirac theory says that the magnetic moment of the electron should be it should be the same as the Bohr magneton there. And G should be 1, and it wasn't. That's what Rabi had essentially measured, was Bright's argument. Rabi was measuring this anomaly, and that so it was 1.00119 differed by about 1 part in 1,000, and it's like, well, what does this due to? Is there something wrong with Dirac? And of course, the person who's going to come up with the brilliant idea of correcting this, and it really was a brilliant idea. I'm just sort of, you look at it and you go, wow, what a great idea. Was Schwinger, of course. So a few months after Bethe publishes his paper, Schwinger comes out with a 1-page paper and proposes a simple theoretical correction to get the magnetic moment, which is 1 plus alpha, the fine structure constant, over 2 pi. And we call the Schwinger factor. And just to, you look at it and you go, oh, that's the most beautiful thing you've ever seen, right? It's a fine structure constant, and it's got 2, and it's got pi in it. It's just, what more could you want? And it was uncannily close to not exactly, but it was uncannily close to the value that Rabi had essentially measured through his measurements. But Schwinger did not explain how he got that, which in some sense, who cares, right? It's just like it's an idea. Let's try it out. But no, he didn't really. How did you get that? And he didn't really detail. He said a paper dealing with the details of this theory and its application is in due course of preparation. By the way, those are both pictures of Schwinger, by the way, and so you were left with this very close match with Schwinger's to the experimental value. And so they said, oh, let's have another conference. Again, Oppenheimer organized another conference, but this time the conference they invited Dirac, Fermi, and Bohr came. Well, they had not been invited to the first one, and they came to the second one, and the topic was going to be is going to be about Bader and Schwinger's work. And say, well, let's see this. What do they got there? So everybody hoped that Schwinger, so this is Consa, everybody hoped that Schwinger would finally explain the elegant way in which the Schwinger factor had been calculated. And so at the Pocono conference, okay, so this is Consa doing work on the history of this, and he does provide citations to multiple references of people's memoirs who were there, very typically. I wish he had been more thorough in with his citations here, because I sometimes found it difficult to say, okay, did this really happen the way you're saying it is? It could have, every sentence could have had a citation, as far as I'm concerned at this point, because we're trying to do physics by talking about physics history a little bit, and we really need to stay close to the vest about what the facts are. So maybe this is all common knowledge. Maybe I'm just the one who never knew this. But so Schwinger's presentation lasted for 5 hours, and Consa adds the words unbearable, unbearable 5 hours. This is one of the reasons Consa's work is a little bit edgy, is he does add these adjectives and modifiers in there like this that are provocative, perhaps in a way that, unbearable 5 hours. I don't know where that word unbearable comes from. Maybe Oppenheimer said that. Series of complex, totally incomprehensible equations. Again, Consa's words. And so Oppenheimer was very critical of it. Others gave talks to show others how to do the calculation, while Schwinger gave talks to show that only he could do it. Now, does that invalidate him? No, it doesn't. It just means that, he didn't have a really good way of presenting why he had come up with that. Again, you sort of want to say, well, who cares? Maybe a good guess can be good, right? But we want to justify it ultimately. We want to find a justification for why that's the value. But a good guess is a good guess, as far as I'm concerned. So gradually the attendees left the presentation. Only Beta and Fermi remained. And Beta had to stick around, right? Because he's the other heretic there at the conference. But you imagine Fermi hanging around for 5 hours, being the last one there. Watching Schwinger try to explain why you got this. So let's see. I got a little hidden here. It was clear that Schwinger's theory was not based on an elegant solution. So everybody left disappointed at his basically his inability to explain how he got that. The next day, Feynman comes up with his. He comes up with the first time introduces the Feynman diagrams in front of the same audience, and Feynman was convinced of the validity of his calculations. He came up with the same value using Feynman diagrams, but the attendees did not respond positively to this presentation. So Feynman, these sentences are out of order. He was convinced of the validity of his calculations because they produced the correct results. And that's Feynman in a nutshell, right? Oh, you don't like these? You don't like these diagrams? You don't like the way I'm doing it? Yeah, but it gives the right answer. It gives the right answer. That's all I need. And that's all I care about, Feynman said. It gives the right answer. And deal with it. Deal with it. So the Pocono conference, Schwinger and Feynman, their theories, this is quote from Beta, who is there, of course. Beta said in his memoirs later, Schwinger and Feynman, their theories seemed to be totally different. Schwinger's was closely connected to the known quantum of electrodynamics. So Bohr was immediately convinced it was correct. So even though Schwinger talked for 5 hours, Bohr, who must have left somewhere along the way because he wasn't there at the end, nevertheless thought this was the right thing. And so that was good, because Bohr was essentially the grandfather of physics at that moment, right? So beta, Feynman came with his completely new ideas, but Feynman, though, didn't get the same response. Among other things that involved positrons going backwards in time. Of course, Feynman published his notes on that back in 1941 in a journal article by Stickelberg. And that's an inside joke, by the way, to many people in the audience will get that. Okay, so because we know that Stickelberg had sort of came up with some of the same ideas that Feynman would borrow, and he did. So Niels Bohr was shocked at this. It couldn't possibly be true, and he gave Feynman a very hard time. These are Beta's words again. So Pocono Conference, after the disappointing explanations of Schwinger and Feynman, the scientists returned home aware of the need for a new unified QED theory that could elegantly explain Beta's Lamb shift results and the Schwinger factor for the anomalous magnetic moment of the electron. So now everybody's like, well, these guys have good ideas, but we don't understand them. We have to come up with something better. And then, as it happened, so Oppenheimer goes back to Princeton, and a paper comes in the mail, and this is such a weird, it's from somebody from Japan, which when you think about it, it's really sort of interesting irony that how this plays out. So it's Tomonaga, Shinichiro Tomonaga sends in a paper, and he has a third way of doing this, and this really was the critical thing that said, well, now something's on here. We got to figure out what's going on here. And Oppenheimer goes on to publish papers with Tomonaga and gets into the game. But the person who is going to, quote unquote, figure it out, at least for the moment, is going to be Freeman Dyson. And so in a paper in 1949, he uses the Heisenberg S matrix, and he comes up with methodology to come up with a infinite series in powers of alpha based on Feynman diagrams, which was the key. So he comes up with this infinite series, and in the first order term, the lowest order term above unity, is exactly the Schwinger factor. And it's like, oh, wow. And the key is that he used Feynman diagrams in this. So explicitly now we have this series where now the Schwinger factor is explained as the lowest order term, and we've got this methodology of calculating in Feynman diagrams that he didn't get a great reception at first, but now everybody's interested in him. And this was really the moment when Feynman diagrams entered the sort of the canon of physics as something you would use to calculate this. So we've got this wonderful infinite series, and so Dirac hated it, though. Dirac hated the Dyson's work. And Dirac, these equations lead to infinities. These infinities ought not to be there. They're removed artificially. Just because the results don't happen to be agreement with observations does not prove that one's theory is correct. So, which is totally against what Feynman's attitude was. Feynman was like, hey, this gives the right value. And Dirac's like, that doesn't matter. This is not physics, he's saying. That's a little strong statement, but essentially that. Then he goes, so Dyson, Dirac hates it, says this is not valid physics. And then, so Dyson goes to Oppenheimer, and he expects Oppenheimer's going to give him a thumbs up because, well, Schwinger was Oppenheimer's student. So I had expected that, this is Dyson talking now, I had expected he would disparage my program as merely unoriginal. On the contrary, he considered it to be fundamentally on the wrong track, a wasted effort. He did not believe the ideas of Schwinger and Feynman had much to do with reality. It was just another misguided attempt to patch up old ideas with fancy mathematics. So you can see Dyson was probably a little bit stung by that because it was very unexpected. So he goes to Fermi, and he thinks maybe I'll bring Fermi all my graphs. He's an experimentalist, and he'll be convinced. And he said he quickly put aside the graphs he was being shown that showed the agreement between theory and experiment. His verdict: there are two ways of doing calculations in theoretical physics. You have neither. So one of them was to follow a physical program, and the other was to have a well-defined mathematical program. As Fermi says, you have neither. And this is Fermi now says, I asked Dyson how many free parameters he had used, and Feynman gave him the answer, and he said, well, a 4, I think he said, or 4. And Fermi comes up with a famous quote. Well, my old friend Johnny von Neumann said, with 4 free parameters, I can draw you an elephant, and with 5, I can make him wiggle his trunk. And so this was Fermi not impressed at all. So the wiggling the trunk, well, let's keep that in mind. Elephant wiggling its trunk. So Feynman's response that really puts him at odds with the old guard. And here you have sort of a generational gap happening in post-war physics. Shut up and calculate, because Feynman, if anything else, what a brilliant man, right? It's hard to say anything against him, and you could say something for him is that he was just incredible genius at calculating, right? So he came from a time and a background where you could spend your entire youth going in calculus books, and so Feynman knew how to integrate any integral, and that was his strength. And what nobody like him since then, maybe, well, maybe there is, but with his scope and his reach and his intellectual prowess that way. So he had a lot of heft, and he's going to win the argument, of course, as we know. Feynman's going to win. But in the meantime, there's the Old Stone Conference, the third and final post-war conference, because Oppenheimer's going to get sort of disillusioned after this about these conferences, and he goes off in another direction. So now we're going to talk about Dyson in the third one. Dyson's now the star, and Feynman, Dyson and Feynman are now the star. And Consa, the star of the Old Stone Conference was Feynman. Now, he used his immense charisma to present Dyson's theory, but the problem was it was so complicated and did not seem to have much practical use at the time. So interest in QED rapidly declined due to its extreme complexity and lack of practical utility, Consa says. I wasn't there at the time, so I trust him on that for the moment. Instead, pions, which had recently been discovered at the synchrocyclotron at Berkeley, became the primary focus, and everybody turned their attention to that for a while. And then you have the real twist happens in 1952, where Dyson figures out that his power series expansion diverges. All the power series expansions currently used in quantum electrodynamics are divergent after the renormalization of mass and charge. Feynman and Dyson says, it was a terrible blow to my hopes. It meant that this whole program made no sense. So the way Consa spins it is that Dyson essentially he repudiates his line of research involving the Dyson series, and he goes back to England and pursues other lines of physics. I don't know. This is an interesting point that Consa is trying to argue in terms of how Dyson felt about his work, because I've watched some videos of Dyson that were made that you can watch online of him talking about this era, and I don't get that impression about him talking about his work. So maybe he's revised his own revision. I don't know. Surprisingly, Dyson's claim that the series was divergent did not diminish QED's credibility, though. And so why is that? Why did that happen? It's because something happened in the meantime between the original paper Dyson put out and then this follow-up one, where he says, well, my series is divergent after renormalization. And that's if there was an updated measurement of the magnetic moment of the electron. In 1949, Gardner and Purcell measured it, and so it had been 1001.19, and they refined it to 146, and now everybody's excited because we have a more refined measurement of that we're fixated on. Oh, let's see if we can calculate this. The Schwinger factor is now outdated. We need some higher order. We need something of higher order, and so using Dyson's series, the Dyson series, Karplus and Kroll in 1950 calculate the next order term in the using the Feynman diagrams in the next order term up, the fourth order term, and which is you've got negative 2.973, and this brings it look at it now. Geotheoretical is 1001147, and and it was measured at 146, and this is now Feynman's great victory lap, right? Because now we go to higher order and we get even in better measurement, and that's what more do you want out of a theory than that, right? And then there was a problem, though. There's only one problem with all this, and this is the point that I think Consa really dwells into, that he really digs into, and was probably the start of his argument in investigating this, is that there was then almost a scandal happened after this in the course of the 50s. You might say in that. So there was an updated measurement in 1956, refined it a little bit to 165. So now the prediction is off by Karplus and Kroll is off, which is not good. So what are we going to do here? So well, in the meantime, Peterman
Matthew,
had found out that.
Matthew,
Yeah.
I think we should soon move to conclusions because
Okay.
people are getting tired. Maybe we'll get kicked out of the building.
Okay, that's what I wanted to know. Okay, so move to conclusions. Okay, so the experimental value, I'm just going to skip ahead. I'm just going to tell you that I'm just going to put out an appeal for anybody else who's read Consa's work. Please, I would love to discuss with you why he might be wrong, because he wants we've got these wonderful theoretical numbers, and if you look at them, and you look at, you just see this convergence. You see the convergence to experiment. And you think, oh, it's all great. He's saying, no. This is, I would say, he believes that the calculation of Feynman diagrams to get these higher order corrections that match experiment are essentially the elephant wagging its trunk. And and he points out, for example, that his big point. I just want to go back. The thing with Peterman discovered was that he corrected Karplus and Kroll, came up with a value that then matched experiment again, conveniently, but he never published it, and we have no idea how he came up with his values. And this is a recurring theme: is we don't know how people came up with their values, and everything now is measured in is done with computers with code that is not published. So I would say tongue-in-cheek conclusions. Consa can't possibly be true because it would mean Feynman's QED is not supported by experiment, but is an exercise in fitting free parameters, chasing experiment to higher orders. So if you go with that route, say, well, he can't be true that way, then okay. But maybe we want a little bit meta reason why he's not right. Experimentalists should prioritize, this is my tongue-in-cheek, experimentalists should prioritize finding ways to continually increase the accuracy of the measurement of electron magnetic moment. And the reason they should do this is to force theorists to calculate and recalculate ever increasing number of Feynman diagrams, the higher and higher order, because this is how we got to keep the heat on here, I think. Because otherwise we'll keep theorists from declaring victory at some high order when we can no longer increase the accuracy of the measurement of the magnetic moment. So we want to make and here's the key thing: can we get a prediction of what the next higher order measurement will be? This is a critique you could make: is it's all retrodiction with very complicated calculations that nobody can repeat and which are never even explained. Now everything's done by computer and nobody even shows their code. Serious conclusions, though. So those are sort of tongue-in-cheek, but there's some there. Consa's work is well researched and interesting to read. He draws strongly worded conclusion. He invites one to disagree with him by his wording. I would say, as a review of the history of the theory and measurement of the electron magnetic moment, it is a great resource. His work is very interesting to read. As a review of the history of QED is also a great resource. I think I started to understand QED for the first time reading his papers. There's a lot of papers I want to read in this one. People doing experiments. Schonship was the program used in the 70s to recalculate Peterman's term, but we don't know the code. Again, very common theme. So answer to the trivia question, I didn't let Richard Feynman get away with that, and I'm not going to let you. I'm not going to tell you the answer, but apropos of absolutely nothing, I'm going to dedicate this talk to the late Cecile DeWitt Moret, who was one of my teachers in Austin. And she was also a pal of both Dyson and Feynman. And there's a lot of the videos online of Dyson talking about palling around with the both of them after the war, going up to Cornell. I like to think of her, in my mind, she's Feynman's bulldog. She was Feynman's bulldog. That's what I may be wrong about that. That's just my opinion, but that's how I envision her. So that is my talk. So if anybody does want to read these papers and talk to me about them, I would love to talk to you what you think about these papers. Very key toss. Thank you. And that is my talk.
Okay. Thank you.